Three, two, one. So welcome back. We continue our first track, and our next speaker is Italo Vietro. Italo is CTO at Lycan. He enjoys working with distributed systems and solve complex problems. So today, Italo will share experience how should we design our systems for failure. So Italo, please start.
Cool. All right. Thank you very much. Cool. It's definitely a pleasure to be here today. It's the first time I'm actually going to give like a conference in a remote environment. So I hope I don't screw up. And I really hope you enjoyed the talk today. So I also want to congratulate all the organizing team. There's a lot of work behind this talks, and it's a great organization so far. Cool. So yeah, my name is Italo, and I work as a CTO at Lycan. Lycan is a healthcare company here in Berlin. We're basically working in the health industry to automate a lot of things on how you take, how you can actually own your health, and you do a lot of different types of tests. And we're basically going towards that and trying to make the German healthcare system even better. So today I want to talk about a few different topics. But the main one, all encapsulated around designing for failure. So how can we actually design systems for the unexpected, right? If you ever thought about it, like your systems today, can they actually, respond if something fails? Can you still serve your customers traffic in case something actually goes wrong? And that's what we're going to talk about here today. So the agenda, we're going to talk about what is resilience. We start there. And we talk a little bit about latency control and strategies that we can use to actually control latency whenever we have a problem in our infrastructure. We're going to talk about isolation and how we can isolate and avoid cascading failure problems. We're going to talk about self-healing and how your applications can come back to life in case they are down. And traffic control, we're going to talk about traffic control and how we can actually control the amount of traffic coming into our infrastructure, a little bit about observability, and service meshes in the end. Before we dive into these very technical topics, I'd like to take you through a journey. So I am a huge fan of aviation. I really like it. And I learned a lot about aviation, and I think the software industry also learned a lot about aviation. So if you think about an airplane, right? And you've probably flown already a few times in the last years. Of course, this year is a little bit different. Corona is here, so it's not happening very often. But in 2019, we had 39 million flights across the world. That's a huge number of flights if you think about it, right? We have a lot of airplanes going on like here and they're flying and they're landing in airports and so on and so forth. But unfortunately, out of those, we had 23 deadly crashes and 28 fatalities overall. And one of them, which is not here, it's actually the case of the 737 MAX. You probably already heard, where software actually had something to do with the problems of the airplanes, and that was actually something that the FAA was actually looking into it. And they came to the conclusion that the software actually interfered with the pilot's capabilities to actually avoid that problem. And this, kept me thinking about, okay, what can we do as software developers to handle failure better? And that was something in Boeing that didn't really happen for a bunch of different reasons. But it's a nice comparison if you think about it. Like one flight or two flights actually, out of those 39 million flights actually went down because of a software failure. That was proven by the FAA. And the reason for this, this high resilience that airplanes have is because they developed something called ELMS. And this is the Electric Load Management System. This is a system that was developed in the 1991, I think, by Boeing. And now it's implemented in a different kind of planes, different models, even in the Airbus and the Embraer. And basically, they have this system which is extremely resilient. So you probably were already flying sometimes, and the plane already failed, and you probably didn't even notice, because there is a lot of backups and failovers inside the airplane that can keep it running without you even noticing. That is the same resilience we want to achieve with our customers in the end. We want to make sure that, problems happen. We are in a distributed system. There is no way to avoid it. And they will happen, but how we can make sure that customers don't even feel it, and that you as a developer probably don't even need to wake up in the night to actually fix something. And the main thing here is that the electric load management system was designed to keep the essentials running, right? So if there is a problem, well, let's think about a 737, for instance. They have a lot of batteries inside. And if one of those batteries actually, fail, they're going to fail over until the last battery is available. If the last battery also fails, all of this is electrical, there's going to be a little fan that comes down of the airplane, and then it starts actually spinning around to give mechanical power and then generate electrical power, so the airplane can keep the essentials running until it can land safely on an airport nearby. This is what I like. And this thing is something that we have to reflect on. There is this quote from Liang Wu where I can relate to that quite a lot. Resilience is a requirement and not a feature. I like to put this into perspective. Whenever we are thinking about a feature or something that we want to deploy to production or anywhere, many times we take resiliency as a something not very important. We develop our product, and we put resilience afterwards, after we have a problem, after we already affected our customers. I did this quite a lot in my career, and I'm trying to change this mindset. I'm trying to change this mindset in our industry, especially in the company that I work for right now. Previously, I worked in N26 and also at HelloFresh here in Germany, and we always had this kind of thinking. Let's put resilience first. Let's make sure that we are more resilient as a team and as an infrastructure. So going forward, first topic that we're going to talk about is latency control. So latency control, we start on the very basics. This is something that you can you can start tomorrow and already put something in your systems. This is the timeouts. This is the simple thing that sometimes we just forget. So there are multiple types of timeouts. I'm going to talk about two especially. So the first one is the client timeouts. Whenever you as a client is calling a third party or another dependency from your service. So imagine that you have a service and you want to call it from your service, right? First thing you're going to do is actually try to create these timeout right here. And simple way to create it, you create an HTTP client. You're not going to use the default client from Go because timeouts are not set by default, and they're not very customizable, but you could set them if you want. But I like to create the client by myself. And then I create the timeout here, 2 seconds, very simple. I create a request, and this site is just simulating like some delay of 3 seconds. And we execute this, and if it fails, and it will fail, we're going to have an error, and we can handle that error and do something about it. This is the most basic thing you can add, and you should add to avoid your service to hang and to avoid your service to not serve requests anymore. Because if you hang, more people will start requesting to your service. Your service cannot serve at some point because you're gonna exhaust the resources, or you're gonna autoscale, but you're gonna end up in a bad place in the end. So client timeouts, always set your timeout. That's the first thing I can say. There's other levels of timeouts that it could set, and you should set if you know the numbers. So you can set actually the timeout, as I said before. You can set the transport layer timeout, which is basically how you're going to connect to the next service. And you can set the dialer timeout. You can set the TLS handshake, the response header timeout, and so on and so forth. Now, how do you actually figure out those numbers? It really depends on a lot of metrics, and we're going to talk about this in the end. So another way you can set timeouts, and this one I like it quite a lot because it gives you a little bit more control and power throughout your application. But you can create a client with no timeout set. That's the difference. you create a context with timeout. And this thing here was introduced very recently in Go. So the new request with context, which is great, because then you can pass a context with cancellation like this one. And again, it will fail because I have a timeout of 2 seconds. And whenever it fails, the cancel will actually be called. And if there is any other requests using the same cancellation, those requests will be canceled automatically, which is great. If you want to do that, of course, then it's great because you cancel all the other requests, you avoid resource exhaustion, and you have a lot of more control. So I'm more lean to use this recently than the other strategy. I'm using more context cancellation with timeouts for requests than setting on the client itself. But both ways is already a good start. So definitely will work quite well. Now, the second type of timeout, that's going to be our server timeouts. So if you're building something like a HTTP server or a gRPC server or whatever other type of protocol you choose, you probably will have to set your timeouts. Why? Because you want to avoid clients actually extrapolating those timeouts. So you want to make sure that whenever you create, in this example, I have just an HTTP server. You want to make sure you set your read timeout, your write timeout, your idle timeout. These three are the very least ones, because then you can actually have control of whenever your timeout is, whenever you're writing to the response writer, your timeout doesn't exceed. Whenever you're reading something from the request, it doesn't exceed. And whenever there is idle connections, you actually want to make sure those idle connections don't pass a specific timeout and can be reused later on. So the HTTP server timeout is something you want to consider to put this. So this is something cool. Now, timeouts, as I said, those are pretty basic, and that's where you should start your resilience, your resilience journey into your services. Of course, there are other strategies, and one very famous, but something that I don't see very much being used, is something called circuit breakers. So again, another learning. Circuit breakers came from the electrical industry, and you probably have one in your home, I hope. And circuit breakers are there to avoid that your circuits running across your house, if there is any problem, it actually opens the circuit, so you don't have any issues like setting your house into fire. So you actually want to avoid that, and to avoid that, you can use circuit breakers. And we do the same thing in software engineering. So, after you map out your dependencies, so let's think about a case where you're calling Google. So in this example right here, I'm calling Google. Google is my external dependency, and I want to wrap it around a circuit breaker, because if something goes wrong with Google, that's unlikely, but it could happen. If something goes wrong with Google, I can handle it, and I can stop sending requests to Google. That's the point of circuit breakers. So in this example, I'm going to wrap this around a circuit breaker. And whenever Google responds anything higher or equals than a status bad request, so for 100, I will trip my circuit and I will do something with it. So whenever I declare this circuit, then you can set this function right here, which is a callback, and you can define your rule for whenever you want to actually open the circuit. In this case, whenever Google fails 3 times and the failure ratio is higher than 0.6, I actually want to open the circuit and stop sending requests to Google. So my application will actually hold those requests in, and it will not go through anymore because the circuit is open. This kind of pattern was very much perpetuated by Hystrix. Hystrix, if there is anybody from Java here that came from Java, they're probably familiar with Hystrix. Hystrix was this library of, it was one of the standards for resilience in Java for a while. And one of the patterns that they had built in was a circuit breaker, and this circuit breaker dashboard that you can see right here. Pretty useful. You can see whatever circuits are open, whatever secrets you have with requests coming in. And this is great. And in Go, that also exists. Although Hystrix has been deprecated by Netflix. This is a pattern that was created by Netflix. And it's deprecated, unfortunately, but in favor of something nicer that I will show in a few minutes. But essentially, Hystrix is something that is called the fat clients. That's how they used to call it. I think the term today in these days is not very valid anymore. But that means basically that they had a lot of things. They were doing a lot of things inside the client itself. So circuit breaking, and they were doing retries, and they were doing monitoring, logging, and a bunch of other things that are useful, but you can offboard that to someone else to do it. So Hystrix was very useful. And today I think they have something called Resilience for J in Java that is also useful, but again, different patterns. I'm gonna show this a little bit further. So circuit breakers by itself can't do much, right? You can open the circuit, great, but how do you close it again? Once it's open, it's open. It's never gonna come back, unless you have something like retries. So let's take a look in this sequence diagram right here. So I have a consumer service. So that is my service that I wrote, service A. And I have a producer service. So whatever I'm going to call it, so Google in this case. So first thing, I'm going to actually try to call it. I'm going to wrap it around the circuit breaker. And I'm going to then wrap it around a retrier. And finally, I will call Google. In case it fails, I'm going to retry the calls and retry and retry and retry before I actually trip the circuit. Once I did all the retries that I can, and I have a threshold, then finally the circuit will open, and then eventually this circuit will be open, but it can close again because of the retrier. So I will retry after, I don't know, after an hour or whatever other rule you have. But essentially, you're going to wrap it around these two things. And you can use a library like Avast Retry Go, which is a pretty simple one, pretty good. There's no extra dependencies aside from it. Or you can write your own. It's not very difficult, but I would recommend just use a library if it exists. Check it out, the source code first. But this one is pretty good. So again, very simple library. It just encapsulates whatever call you're going to do. You set your retry amount, so how many times you actually want to retry. And you set your delay type. So your delay type really depends on your strategy. You can have something called exponential backoff, which is one of the most used today, where you're going to call Google and it's going to fail. And you're going to retry in 2 seconds, let's say. So you retry and fails again. You don't want to retry in 2 seconds again, because very likely it will fail. So you want to try in an exponential time. So you want to try probably in 4 or 8 or 6, 8, and 10, and so on and so forth. So that is the exponential strategy. You can implement your own strategy, or you can use whatever linear strategy you have, 2 seconds, every 2 seconds, try again. Or you can use whatever other strategies. There are a bunch of them in the library, so you can just check it out. But with this, you finally implement retries in your application. So these plus circuit breakers, now you have a very, very powerful thing. Right. So next, we talk about isolation. And, whenever you have a cascading failure in your system, if you ever face this, probably you probably already complained a lot, because it's very hard to point down where the problem is, especially if it's a cascading failure. So you have service A calling service B, calling service C, calling service D, calling a database, and the problem is actually on your database. Everything from this tree here is actually going to fail. So all this link will be your weak link, and it will actually fail. So tracing this down, unless you have a lot of monitoring going on and a lot of tracing going on, it's going to be a headache. And what you want to do is make sure the service that you write are isolated enough so you don't have problems. So one strategy is called bulkhead, and not many people know this strategy, but I like to tell you another story from the Titanic. So I hope you all know the Titanic. So Titanic actually set sail in 1912, I think, more or less, 1912, and sank in the middle of the Atlantic because it hit an iceberg. And, there was a design failure in the Titanic. So bulkheads come from the naval industry. And in this GIF, you can see here this yellow bars right here. Wait a second, let this come back. Please come back, please come back. There we go. So these things are the bulkheads. And these 4 things here is where the iceberg hit the Titanic. Unfortunately, if you ever watched the movie or ever read anything about the Titanic in detail, you're going to see there was a design failure with the bulkheads. The water went in, and the point of bulkhead is actually isolation. So it needs to isolate whatever is coming in, fire or water or any other liquid or problems that you have. Unfortunately, the water went up into the bulkhead, and there was a design failure with the air that was passing through the chamber itself, and the water went to this air duct, and then went to the next chamber, which is the bulkhead, and went to the next chamber and the next. Unfortunately, the Titanic could only hold the weight into like 4 or 3 or 4 compartments, and it went to 5, and the weight was too high to actually hold it on, and it broke in the middle, and that's the rest of the story, probably. So again, in software engineering, and especially calling third-party services or databases or event streams like Kafka or anything like that, you can do a bulkhead around it. You can make sure you can isolate calls to that. In Java, that was used to be done by Hystrix again, with a thread pool, simple thread pool. In Go, we can replicate that quite easily just by using something like a pool of Go routines, right? Go routines are much more powerful than threads itself. So that's good. We can spin up as many as we like. And you can also isolate them and do a pool of Go routines, and then actually use that to isolate any external calls. So in this example, this is part of the implementation. It's not the whole implementation. You can check it out, this library here called Heimdall. It's a cool library that has some, it's sort of trying to replicate what Hystrix did, but in Go. I like to look at the implementation. I don't actually use it because I use something else, but this is a cool library for studying, I think. And they have this Hystrix do here, which isolates this call into a Go routine. And around this code, there is a lot of retries and circuit breakers and things that you can use. Whenever this fails, your application won't hang because it's, of course, encapsulated in a Go routine. And that's what you want. You want that if it fails, you don't block the main resource, which is our main thread or main Go routine that is actually executing your code. So by not doing that, you still serve your requests, you still serve your clients or your customers, even though an external dependency actually failed. So this can be achieved by bulkheads, and that's the whole point of it. You see, if you want to see the whole implementation, I definitely recommend you go into Heimdall right here, which is great, and you can study a little bit more. And of course, check it out, the Hystrix specs from Java. I think it's a very inspirational thing when studying a little bit of resilience. So really cool stuff. Now, self-healing applications, right? So you have all of these patterns, that can actually encapsulate and prevent failure or try to prevent a bigger failure. But how do you actually try to recover from a failure? And for that, you need self-healing applications. So first thing we start with is always health checks. Health checks are normally used by, load balancers or schedulers. Schedulers, what I mean is basically container scheduling. So if you use Kubernetes or Mesos or any other Nomad, for instance, they have schedulers. And the schedulers normally look at your pods or whatever they call it, and they're actually going to see your health checks and see if your application is healthy. So the main challenge here is actually figuring out what to measure and what is important for your application to run. So think about your applications today. What is essential for them to run, right? Which kind of dependencies you have in your applications that are essential, and it has to be there, otherwise you can't serve traffic anymore. If you know those, that's already like a huge plus, because my main problem was always figuring that out, like what are actually the important dependencies of my application? And if something is not important, how can I actually make it not important, right? And make sure my application can still serve requests. This seems simple, but it's actually very challenging to figure it out. So in this example here, it's very Kubernetes oriented, but still can be applied to any kind of scheduler. So you could apply to Nginx, you could apply to HA proxy or whatever other load balancer you choose. In this case, I just set a liveness check right here. This number is completely arbitrary. It doesn't need to be this one. It's just for an example. And I have this readiness checks right here. So I just set up, okay, this is my readiness check. My database is important. My payment service is important. And Google, for some reason, is important. So whenever this is down, my application is actually going to return something like this. So if everything is okay, if everything is okay first, you're going to actually have this return and a 200. So with the 200 is actually what the load balancers or schedulers are going to look at to make sure your application is healthy. In case something is broken, then you're actually going to have this in the end. You're going to have a 503, and the schedulers are going to try to bring up your pods or whatever it is back up, or schedule a new one and take the unhealthy one out, right? So that is the whole point of having this self-healing kind of thing. Of course, you depend on something else to heal you, and that's the schedulers or the load balancers. We have something called outboxer as well, which is a pattern that it's not used much in Go. At least I never saw it being used that much, but it's used a lot in the C# community, and it's super easy to implement in Go. So basically, this says if you have let's say a message broker like Kafka, for instance, or RabbitMQ in this example, and you're a producer, right? You're producing a message, and RabbitMQ is not there anymore. What do you do with that message? Do you drop it? And if you are in the middle of an important transaction, you just return an error to your user, or do you save it somewhere else and try to reconnect to the dialer of MPQ and send it again? So that is the whole point of the outboxer. You have a primary storage, like a Postgres database. You have a AMQP here as an example. It could be Kafka or something else. And then you create an outboxer where you pass a data storage, you pass your event stream, and you pass a few configuration points like intervals of how often you want to try to reconnect to that. Now you have a common interface that you can send your messages, like a send message like this. And you set up your message, you put your payload, it's just a slice of bytes, and whatever extra information you want. And in the end, if the message broker is there, it will just send as normal. But in case it's not there, it's going to save on your primary storage. And then it will try every, whatever I said here, whatever minute or second, or 5 seconds, it will try to send a message again and see if the broker is there. In case it is, it will try to send it and will probably succeed. There is a lot of discussion about this pattern of, okay, but then you're just offboarding your responsibility to the database. What if the database is not there? Well, then I think you have a bigger problem already. Your dependency is actually your database, but the message broker is not essential. So that's something you might want to consider. There is this implementation I've made in Go. It's just something that I like to play around with. So if you want to check it out, please do. I would definitely appreciate it. So we go to traffic control here. And there is one thing that probably a lot of you are already related to called rate limiters. And rate limiters are great to actually avoid, overloading your service. Circuit breaker, you want to avoid overloading the upstream service. In this case, you want to avoid overloading yourself. And you can do this in multiple forms. So circuit breakers, rate limiters are super useful if you just do, you can easily define this. This is a cool library for rate limiting. You can write your own again, super simple. But the main problem of circuit breaker of rate limiters is because you have, you are storing this in memory right here. What happens when you have multiple instances of that? That is when the problem actually becomes apparent. And for that, you're going to need distributed rate limiters. And well, with any kind of distributed problem, you're going to have a centralized, point of failure. But Redis could be something resilient. You can use Dynamo. You can use whatever data storage that is distributed with low latency. You can choose, and then you can use the same library just to set up your Redis limiter, and then make sure that whenever you have multiple instances, all the counters for the rate limit will be in sync. And finally, you can provide the same kind of count throughout your app. So rate limiters are more for that kind of thing, and you want to avoid having these problems. Most of the load balancers or most of the the edge layer kind of applications like Nginx, HAProxy, Envoy, whatever, you normally have that already implemented. In Envoy, for instance, they have only the in-memory version of it, but you can easily write an Envoy filter that will then have a distributed rate limiting. So this is super cool, something that might be worth to study a little bit more if you want to protect yourself from external calls. Right. Nothing that I said so far is useful if you don't have observability. So it's nothing like that is useful. And the first thing you should have, even before considering applying any kind of this standards or patterns, is actually having metrics in place. And not just metrics. Whenever you have multiple services, you want to make sure you have standard metrics across all the services. If you have like 100 services and each one is throwing different kind of metrics, you might have a problem consolidating those on Grafana later on, or whatever Datadog, for the sake of it. So you want to make sure you standardize that. And there is something very cool that is in the industry today. And the same is valid for distributed tracing, the same kind of pattern. You want to streamline this. You want to make sure it's standard. And the pattern is actually called, it's called distributed tracing. So we have this here, open tracing, this one. And this one is open census. So if you never heard about this, I definitely recommend you read it, because open census and open tracing are two standards that were created for standardizing metrics and tracing across any kind of application. Doesn't matter if it's Go or Java or C# or PHP, whatever it is, you can standardize it on the same way and report metrics in a uniform way and create unified dashboards for analyzing your data. So again, this is easily done like this. You create a exporter. In this case, I'm creating a Prometheus exporter, and I'm going to report metrics across my application in a uniform way. And let's say that I want to change from Prometheus to Datadog. So I just come here, I replace this reporter by Datadog exporter, sorry, and there you go. You have all the metrics that are already in your code being now exported to Datadog. Same is valid for distributed tracing. In this case, I use Jaeger. And let's say that I don't want to use Jaeger anymore. I want to use Zipkin, or I want to use StackTrace. I can just replace the exporter, and the whole tracing in the application will actually remain the same. I tested this myself, especially where I work today. We were on Datadog, and then eventually we wanted to have Prometheus. It was just a matter of changing this in a single place. So that is extremely useful when you actually have to change your tracers or metrics. And there is something now new called OpenTelemetry, which is coming soon. I think it's already on beta. You can already use it in Go in the beta version. I think the final version will come out very quickly. And OpenTelemetry is exactly the consolidation of these two things, of open census, open tracing, finally in a single unified API that you can use across your whole app, which is great. It still works with a bunch of clients for different SDKs, actually, for different languages. And that's a lot of things, right? Up to now, we saw different patterns, and you probably are asking yourselves, well, Italo, cool that you showed me this patterns and everything, but I'm not going to write this. Like, it's a lot of things. I have like 50 microservices, or I have 50 services across my whole architecture. If I'm going to write all of these in each one of them, it's going to take forever. And that's right. It's going to take forever. And that's what Netflix and other big corporations actually realized with the clients that I mentioned before, the big old clients that are doing too much. And there is something called Service Mesh. And Service Mesh uses a different approach called sidecar approach. And I have a lot of experience in Istio and Kubernetes, which is great. But the thing here is, I'm not here to say if service meshes are good or bad. I'm just saying it's a strategy to actually make implementation of resilience a little bit better. There's a lot of discussion in the community saying, wow, service meshes is bad or service meshes is good. I'm not diving into that. It's just too much. But here I want to show you a different approach for how you can actually implement resilience in your architecture, if you have a big one, if you have a complex one. And the way it works with Istio specifically, but also this architecture is similar to all service meshes, is that you have a sidecar right here, and in this case, it's going to be Envoy. You're going to have like service A, service B. Every time service A wants to talk to service B, it won't talk directly with service B. It will be proxied through a sidecar, which will then apply a bunch of rules, and it will then call the service B proxy, and then the proxy actually calls the service B. And the same goes like from outside requests and going to the egress requests to your external dependencies. Everything is going to be going through a proxy, which is what you want, because you're going to offboard a lot of responsibilities to the proxy itself. So here's a few things you can do with Istio that I showed before with Go. You can do the same in Istio, like timeouts, as I said. Like pretty simple timeout here. I'm just saying 10 seconds. Every time someone tries to call my service, call ratings, I'm going to actually have a timeout of 10 seconds. Meaning in 10 seconds, well, you can handle the failure on your Go program because you will actually see this returning an error. So you can set the timeout here, and this is going to be distributed across your whole namespace if you want in Kubernetes, or across your whole cluster if you want, the same rule. So much easier than having to deploy a new version of your apps across all of that. Same is valid for retries. So you can set up the retries right here. Same is valid with circuit breakers. You can have even circuit breakers being done by the proxy itself, so you don't have to code everything yourself in your Go application. And one extra thing that service meshes normally do, it gives you this nice visualization of your whole mesh, which is great, because then you know exactly what's happening across your application. If something fails, you're going to see a red line right here, and you know exactly where the problem is. And you still know, because metrics are going to be integrated here, if you are still serving requests properly to your customers. So looking at this, looking at service meshes and looking at the other strategies that you can apply to your applications, I like to combine a little bit of both. So today at Lycon, we use something called, we use Terraform to actually create our repositories in GitHub, for instance. And whenever someone wants to create a new service, they actually use this module right here that we created. They create the new service. And especially this area, they have this template right here where you can just set up the organization and where your template is. And this Go template is going to have a few things that we use, like open tracing and open census. But everything else, we don't implement in Go anymore. We use Sidecar for that. Of course, in this template, there's a few more things. We have all the Helm templates that we deploy. We have extra things for our company that are very specific to our domain that needs to be applied across all the services. But basically, this is a super easy way to create a service out of the box. And then, boom, it's there. It works. Simple as that. So to recap, we talked about resilience and what it is. We talked about latency control with timeouts and circuit breakers and retries. We talk about a little bit about bulkheads, and I encourage you looking a little bit more about it. I also talk about health checks and outboxer pattern, which is extremely cool. And we've also talked about rate limiters, observability, and service meshes. So I definitely encourage you to take a look at these two projects. So this is my talks if you want to check it out. Check the coffee shop. I'm a huge coffee fan. And in this coffee shop project, you have all the patterns that I described here today. They're implemented there in Go. You can check it out. If you want to study a little bit more, I recommend this Microsoft project, which is great. And you can check it out. And please follow me on Twitter if you want to ask me any extra questions. And I definitely thank you very much for your time. Really appreciated that you are here in the talk today. I hope something can be carried on to your careers. Thank you. I am probably supposed to say that I'm finished. Hold on. There we go. Go. Thank you again.
Thank you very much. It was super interesting talk with many, many details. But really, we slightly ran out of timing. So really, I don't have I don't see any questions. I have one from my side. So how to handle context canceling on the server side? Imagine you have the service A, the service B. So you told us how to handle context on the client side. So you cancel the request, but the server doesn't know anything about this cancellation. So he can continue to do some work that isn't required anymore.
Right. So normally, if you look at the server creation, the HTTP server creation, there is something called the base context. This is something also very interesting. And you can set a base context that will be replicated to every request that comes in to your server. And you can set the context there to be anything that you like. You can have cancellation. You can have timeouts. I'm not a huge fan of using server context cancellation on the server side, because you normally don't have this, this communication both ways unless you use gRPC. If you're using gRPC, then for sure, it's great to have cancellation on both sides, because then you can control the whole flow. But if you're using standard HTTP server, I wouldn't much use service cancellation with that request, with that regard. But it's something that you could do with the server, the base context that you can set up for sure.
Cool. Yeah. Thank you.
Cool.
So if you have any questions to Italo, please go to the speaker's room and ask him. So thank you again. Yeah.
Thank you very much. I appreciate it.
Yeah. Thank you.
Ciao, ciao.
So we can repeat like this, like
Cool.